So, this kind of differentiation that we're talking about today is called implicit differentiation. We'll talk about why it's called implicit here in a second. But if y equals some function of x, such as y equals x squared plus sin x, this is what we've been used to seeing. There is said to be an explicit relation between x and y. Basically, it means that y is easily solved or isolated. So y is already by itself, but if it was on the right side, it'd be easy to get it by itself because there's just one y in the whole problem, and it's not squared or cubed or anything. It's just y by itself. If x and y appear in an equation like this, then it is implied that y is a function of x, but not particularly written that way. It is then said that we have an implicit relation. So implicit is called that because it is implied that y depends on x. But it's not clearly written that way because we don't have y equals. In this objective, we're going to learn how to differentiate y with respect to x without first isolating y in the equation. Okay, because we're going to have equations that we can't necessarily isolate y easily. We're going to talk about, or look at a beginning example of an implicit relation, and then talk through some steps after we go through this example that apply to every situation. Now, first looking at this graph, what shape is that? A circle. And is that a function?
No.
Why is it not a function?
The vertical line.
The VLT. Okay. So it doesn't pass the VLT, so we can't say this is a function, but we can say it's a relation because it is a set of x and y points that, in this case, form a circle.
So is this more coordinate geometry?
No, not really. No. All right, so explain why the graph is a circle. Well, in this case, it's a circle because all points on the curve are how many units away? 5. So all points in the curve are 5 units away from the origin. Why would we need to know that in order to say that this is indeed a circle? Donnie?
Because the circle is equal at all points
from the center. Yeah, any point on a circle is the equal distance from the center. And what would we call that distance in a circle? A radius. Okay. So all points on a curve are 5 points away from the origin, thus forming a circle. Okay. Now, they tell us to differentiate implicitly to find dy over dx. This is a form of notation that means the derivative It's called Leibniz notation. It's just a different way to write derivatives. So instead of saying y prime, we would use this. The reason we have to use this in this scenario is because y is not by itself. So we can't say y prime equals blah, 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 because y is in a different spot here. It's not y equals. It's a different function.
Move anything out of the
We're not going to move anything. And this is why implicit differentiation is nice, because you don't have to try to get y by itself. You can differentiate without messing with the function at all. So we're going to start with x squared plus y squared equals 25, our function for this, or our equation for this circle. Now, when you derive implicitly, which is what we're going to be doing here, everything stays the same. You take the derivative of every single term, moving left to right. The key is whenever you take the derivative of a y, you have to include dy over dx to show that you have taken it with respect to x. For example, if you take the derivative of x squared, what is the derivative of x squared? 2x. Now, you're taking the derivative of x squared with respect to x. So if we were going to write it in Leibniz notation, you would have it as dx over dx, but that's 1, essentially. So we write it as 2x, and we don't include the dx over dx to show that we took the derivative with respect to x. But when you take the derivative of this, what's the derivative of that term? 2y, but because it's a y, you have to include this notation to show that that's the derivative of y with respect to x. Yes?
Now, why is it that we're finding it in respect to x?
because it's implied that x depends on y.
So
Like every other function that you've taken the derivative of, it's always been.
so an implicit relation is when x is the dependent
Right.
and y is
Like, for example, if I had the function y equals, I don't know, 2x squared, and I told you to take the derivative of that, usually you'd say y prime equals 4x, right? But we could also write y prime as dy over dx because you're taking the derivative of y with respect to x. It's saying the same thing, but there is a reason why we're going to start using dy over dx more now to represent the derivative, because it will help with some other objectives that we have coming up.
Does the d actually cancel each other?
Derivative of.
Derivative, so it'd be the derivative of y divided derivative of x.
Not divided. It's notation that represents the derivative of y with respect to x. Okay. And then what's the derivative of 25?
0.
0. Okay. Now, at this point, if we want to find dy over dx, I have dy over dx as a term now. So if I was to get that by itself, can I probably do that at this point?
probably could.
Probably could. So if I want to get that by itself, we'd have to subtract 2x from both sides. And then do what?
Divide by 2y.
Divide by 2y. And I get negative x over y. Because the 2's will cancel.
So the derivative of a circle, no matter the radius, is negative x over y.
Correct.
Oh, sweet.
Well, sometimes with a circle, there'll be numbers in front of x and y.
But doesn't that make it a ellipse instead of a circle if that's the... No?
Depends on what the number is. Alright, so we're going to calculate the two values of y when x equals 3.
What does that mean? Like, do we plug that into the into...
Well, what does that mean? If I want to find y when I'm given an x, what function am I going to use? Am I going to use the derivative or the original?
Derivative.
I'm looking for the derivative, or
The original.
am I asking for a rate of change here, or am I just asking for a value of y? I'm going to use the original then. I'm just looking for a value of y, so we're going to take 3 and plug it in.
Stop listening to her.
Excuse me. Okay, that's me. Next.
Couldn't we just say that
Ladies and gentlemen,
since it's 5 all the way around, couldn't we just say that it's 5 or negative 5?
no, because this y value isn't negative 5 or positive 5. It's a distance of 5
It'll wind up being
Oh,
square root of
from the origin. Alright, so y squared is going to, what's 25 minus 9? 16? Okay, so you get y equals plus or minus 4. So this is, again, why this is not a function, because when you plug in 3, you get two different values. So let's go ahead and mark those. 3, 4, and 3, and negative 4. We're supposed to draw a line with slope dy over dx through the point found in part C with the lower value of y. Okay, now I know that sounds confusing, but sometimes they ask you weird questions like this. So, if we were to draw a line with slope dy over dx, because what is dy over dx represent again?
The derivative.
Derivative of...
Right, the derivative is the slope of the
Of the tangent line.
tangent line. Okay. So, I want to draw it through the point found in part C. Well, I found 2 points in part C. So, I want the one with the lower value of y, which is the
3, negative 4.
the negative 4. So, it's going to be this point here. So, you're going to draw a tangent line in, and then we're supposed to value.
So do we need to plug in our lower point into the derivative of the circle?
We will here after we draw on the tangent line. Okay, so you draw on the tangent line because it has a slope of dy over dx. To actually find the slope of dy over dx, you would take that point 3, negative 4 and plug it in to the slope here. Now, this is different or slightly different than other problems we've done with finding rates of change at certain points, because almost every other time we've only ever had to plug in the x value. But now, because my derivative function includes an x and a y, you need to be able to plug in both of them. Okay, so the slope of the tangent line, or the rate of change at that point. 3 negative. Okay, so you draw on the slope of or you draw on the tangent line. Does it look like that tangent line would have a slope of 3/4? I mean, at least it should be positive, so we have a positive slope there. But that is the slope of the tangent line through that point with a lower value of y. And how is this? I think that should be rate related to the graph. And I've said it several times, but this is the slope of the tangent line at x equals 3. I should just say at 3 negative 4. Okay, so implicit differentiation is going to use skills that you're already comfortable with. One of the key things that we're going to have to pay attention to is when you take the derivative implicitly, it's for functions that you cannot get y by itself easily. And you just go left to right and take the derivative of each part. But whenever you take the derivative of something that has a y in it, you always have to include a dy over dx. Yes?
So when you have an x value multiplied by a y value, if you have...
You have to do the product rule.
So if you take the product rule that you have to have
When you take the derivative of y.
over dx, do you have to distribute that through two parts, or can you just leave it outside of parentheses?
You leave it outside of parentheses. Alright, so flip. The guidelines at the very top here are going to be what you need to write down. Again, this is for functions where we cannot get y by itself. And I should say functions. These are for equations where you cannot get y by itself. And you're still asked to find the rate of change at a certain point. So we're going to take the derivative of both sides of the equation with respect to x. And all that means is that whenever you take the derivative of y, you have to include dy over dx. Then the second step, after you've gone through and you've taken the derivative of each piece of it, you're going to have dy over dx's kind of throughout, because they'll appear every time you take the derivative of a y. So our goal then is to collect all the terms containing dy over dx on the left side of the equation. So anything that has a dy over dx attached to it gets moved to the left, everything else gets moved to the right.
And it gets attached to on every y, right?
Yeah, anytime you take the derivative of a y term, then it's included.
Why would it matter what side of the equation you want?
I mean, you can do it on the right. We usually do it on the left. Because that way when we do the third step and you factor out that term dy over dx, it's easier to say dy over
Just
dx
if we
equals.
rethink about derivatives.
I just didn't know if it didn't work on the right for some reason.
I mean, it would. We just rethink left, right. So as we're doing this implicit differentiation and doing some of these examples, don't forget about the rules, like product rule, quotient rule, chain rule, power rule, because all of those still apply. So when you're taking the derivative as you go left to right, in step number 1, you're still looking for those cases when you're going to have to use the product rule, the quotient rule, or some of those other ones. Okay, it's just extending out the past a little bit. Okay, don't write that down quite yet.
How many?
Switch to example 5 for more reading.
Yeah, that's my note.
These are gonna take that measurement.
Yeah.
Alright, so let's go with, go to example 5. Skill switch. because example 5 is the one that takes a little bit more space than I gave you. Okay, we're going to find the derivative. And keep in mind that dy over dx means the derivative of y with respect to x. And this is the equation that we're going to be doing that with.
So the equations that we've been doing weren't of y with respect to x?
No, they always were. It's just that when you took the derivative of y, it just became y prime, or dy over dx. Like we only ever had one y, and now we're going to have more than one y.
So before, what were you? Before we were still taking the derivative.
You were still technically doing this process. It's just we never had to move anything over because we never had any y's on the right
There was
side.
only one y.
Right.
This is kind of like algebra then.
Hmm?
This is a little bit like algebra then. Combining like the
Yeah.
derivatives.
All right.
Like just type logic.
So this is as simple. This is as simple as they're going to get, because if you look through this equation, I don't have, like, I have y to the fourth, y squared. Do you see any like two functions or two variables that are multiplied together or divided or no? So this is pretty much as easy as it's going to get, because you just have to use the power rule as you move left to right. This is just to help you see how doing implicit differentiation is a little bit different.
So you just put it's literally the same thing except you just put the dx dy on it.
So when you take the derivative of 3y to the fourth, what's the derivative of 3y to the fourth?
12y to the third.
12y cubed?
Dx over dy.
Yeah. Since you took the derivative of a y term, then you have to include dy over dx. Derivative of y squared would be 2y, but again, you have to include dy over dx because you took the derivative of a y term. The derivative of negative 2y would be negative 2, but again, include that dy over dx.
So it only gets harder from here on out.
Well, just because I start making you do like product rule and quotient rule and that kind of stuff in it. Negative 3x squared, what's the derivative of that?
Negative 6x.
And the derivative of 4?
0.
Now, I will tell you that a lot of people forget to take the derivative of the right side. Make sure that you do everything moving left to right. Now, the next step is to collect all the terms that have dy over dx on one side and move everything else over to the other side. And I kind of do both steps in one. If I was to move this to the other side, we would just add 6x, right?
Yeah.
And then notice what we would have left. Each term would have a dy over dx in it.
Pull it out.
We'd pull it out as a greatest common factor. So I kind of do the moving and the factoring out kind of all in one step to save room.
It's not always going to be this easy, is it?
No.
Oh no.
No.
Never is.
So I pull out the dy over dx, and I'd have the 12y cubed plus 2y minus 2 equals 6x. So is everybody okay with me doing kind of both steps in one?
Yeah.
So we can kind of see how that happens. And then if I need to solve for dy over dx so that I have a problem like I've seen before, where I have like y prime equals something, how do I get dy over dx by itself now?
So you
You divide it by that stuff. Or you get
Divided by 12y.
that stuff over.
We divide it by whatever's in the parentheses. Yep,
Yeah.
just get rid of the whole thing. So we're going to divide everything by this.
She gave me that teacher's
We're going to divide everything by that expression. So you end up getting dy over dx equals 6x over 12y cubed plus 2y minus 2. So with implicit differentiation, your answers will have y's in them. But that's okay.
Will they have hows?
That's okay. I do not
wait, so
like
is this
those.
the answer?
Will they have hows?
It's weird.
Usually
My mind doesn't want to accept this.
Wait, so is
5
all
hows.
all this implicit differentiation or whatever you call it?
differentiation.
Okay, good.
Math and
I
English
feel
are
like
very
Is all it is just moving stuff
math
around?
and English are
Yeah, and the included piece of whenever you take the derivative of something that has a y in it, you have to include dy over dx.
Okay, so I mean,
All right.
essentially there's really not much math involved. Like
No.
Well, it's stuff you already know how to do.
No.
yeah.
And they keep running opposite.
Okay, let's go to example 3. problem that we're going to do tomorrow. Now, to give you a clue of what we're going to do tomorrow, we're going to be doing the rest of these notes in class and then just practicing the rest of the time on implicit differentiation with partners or whiteboards or whatever I feel like doing. And then you will have a homework video tomorrow. And you will have one also on Friday. Maybe I'll make it 2 this weekend.
Cross. Go for it, but you don't have to guess the game theory.
What?
Mine was a joke. I was like, do it, I dare you, but you don't have to guess the game was 3.
What was it only it's like a minute long. It's a determine the slope thing.
You know what I'm gonna do? I'm gonna make her really upset. Like the last
Why?
day we're here.
Why is it your...
And then you just go, fine, I'll give you an extra homework assignment. I'm like, do it, I dare you. I'm like, you leave. It's like, okay.
Why is it my students' goal sometime to make me upset? I mean, one year, like, I had a student that was like, I'm going to make you mad at me this year. I'm like, well, first of all, you shouldn't have told me. You should have just tried. That probably would have happened, but why is it my goal?
You could have just gone over on your desk and put all those really nice folders and just went.
When I was in Spanish, last year, my entire class tried to make Ms. Rude cry.
Why? It's so horrible.
Yeah, they were trying to make her cry, but like they were doing it by just not saying anything, not participating at all. She's like, okay, I don't know what's going on here. She's like, but I don't mind. She's like, I have work to do anyway. So then they just stopped. They're like, oh, it's not working.
It's like we're helping her out.
Yeah.
Yeah, let's not try to make me cry or mad, because that's not fun.
Just go into class and be like, you know what, I'm gonna make the teacher cry. You walk in, the teacher cries.
I don't understand that. I know.
Just
I'd like to wish all the wrestlers
So no homework tonight.
in the States good luck. Bring home a
Oh, wait.
championship,
Send me you
wrestlers.
guys across?
I got wrestling tomorrow.
When were you going to tell me?
Here at Richard
You weren't going to tell me, were you?
No, I was at
Oh, Luke was. Goal wasn't.
And
Thank you.
So if we just watch the videos.
the students
I mean, are you going to have
in
access to
Europe,
stuff?
there's an
Yeah, we'll have
informational
it.
parent meeting tonight
Okay,
at 7
so,
p.m. at Conference Room after
watch the
class.
videos, take the notes, and if I have worksheets I can send you.
Also, all teachers,
Are you going to be able
lunch
to get
is
email?
already here in the
Stop,
office.
you don't have internet.
Yeah.
What's your email address?
Mine's creagan2012@gmail.com.
And Luke?
LukeReagan@yahoo.com.
You guys are
Kim,
so creative.
to the office, please.
At Hotmail?
No, at
Do you know
Yahoo.
you're
Yahoo.
recording still?
Alright, so if we do like practice in class, I can send you. I will do that.
Sounds good.
Everyone's gonna know your email now.
You're gonna get spam email.
Answer the last part of my test.
Yes. Is it one that you turned in